Today's lesson's over section 3.9, talking about linear approximation and differentials. So linearization is as we're looking very close to like a tangent line and that point where they touch between a function and the tangent line. As you move in closer, the actual function starts to look more like the tangent line and becomes more linear. And so in some situations, it's actually easy to calculate the function at a, but difficult to be able to calculate things near a. So using kind of this picture here, we can kind of rewrite or write a equation for the tangent line using approximations. And so using the slope intercept form for just a linear equation, since I know a point of a comma f of a, I'm able to plug that in. Remember that the tangent line is actually representing the derivative, so m is the same thing as f prime of a, and so rewriting it, I can find a linearization or a linear approximation equation, which we'll call L, to help me approximate points near a. So for example 1, here, sometimes they give you kind of expressions where you have to decide what the f of x is supposed to be based on what they're doing. So since they're wanting you to estimate 2 to the 0.1 power and 2 to the 0.4 power, our function should be 2 to the x. And it's always like your a value that you're going to be talking about is always going to be close to those values, which is a value we should know or we already know. So if I plug in a being 0, those are very close to 0.1 and 0.4, plus I definitely know what 2 to the 0 power is. So I first want to take my function, find the derivative. Remember that the derivative of something to, like a number to a variable exponent, is that times the ln of that number base. And so I'm able to get 2 to the x times ln of 2. And then f of a is the same thing as 2 to the 0, which is equal to 1. Plugging in our a, which is 0, into our derivative, and allows us to find ln of 2. And then from there, I want to plug it in so I can find my linear approximation equation to estimate that tangent line. So I'm plugging in the f of a plus my f prime of a times x minus our a. And so I can reduce a little bit. Since it's x minus 0, it's really just x. And so I can just move that to the front. You can rewrite these however you please if you want to keep them as they are, like in the previous step. But it makes it a little easier to kind of simplify and find those values. So now I need to actually approximate those. So my values that I'm going to plug in are 0.1 and 0.4. And that gets me 1.069. When I plug in 0.4, I'm able to get the value of 1.277. Okay, and those would be my answers. Okay, moving on to example 2, it says let f be a differentiable function such that f of negative 3 is equal to negative 9, f prime of negative 3 is equal to 5. What is the approximation for f of negative 2.85 found by using the line tangent to the graph of f at x equals negative 3. So here, they don't really give us a function, but they do give us what f of a and f prime of a are. They also give us what a should be, which is negative 3. So using all that information, I can go straight to plugging it into the ln of x equation that we have. And then I can simplify this one a lot easier than the last one because it's got some like terms that I can put together. So I'm able to get 5x plus 6. And then I'm able to plug in negative 2.85 into the function that I created. And that allows me to get the value of negative 8.25 for my answer. Example 3 is very similar to this last one, except they give me a function. So I have to do a little bit more work, kind of like what we did in example 1, to be able to find our approximation for here. So we want to be able to find 9.2's approximation. Our a will be 9. Using the function of x to the 3/2, I take the derivative. Gets me 3/2 times x to the 1/2. F of a, now I get to plug in 9. Remember, I can rewrite that so it's the square root of 9 to the 3rd power. That gets me 27. Plugging that into the f prime of a, square root of at 9 would be 3, so 3 times 3 halves gets me 9 halves. So now I have all my info. I can plug it into my linear approximation equation. And doing some simplification, I'm able to get 9 halves x minus 27 halves. And so now I can plug in that 9.2 into my calculator to find my answer. And that gets me the value of 27.9. Okay, have fun.